Hello, everyone. I'm Jiahao Chen from iPads Lab of Shanghai Jiao University. Let me introduce our work, CPC, Flexible, Secure, and Efficient CVM Maintenance with Confidential Procedure Calls. In short, a confidential VM is a VM in the TEE, so that the host OS cannot access its internal data. Like other TEE, the boot images can be attested by the guests. The internal register states of CVM are also no longer directly accessible to the host as traditional VMs. In addition, the private memory of a CVM is isolated by an extra stage 3 memory protection and is also not accessible by the host. The VM exits are also filtered by the trusted firmware, so that the host cannot get extra information from the parameters. Current hardware vendors are actively exploring CVM solutions. For example, AMD SEIEE has been in commercial use for a long time, and some organizations may have already tried the Intel TDX. ARM CCA and the RISC-V CoV are also coming soon. While CVMs safeguard the privacy of cloud tenants, they present grand challenges for maintenance. On traditional VMs, the host can intrusively access the guest memory. Operations such as snapshot and migration can then be transparently implemented. Part of the operations require the internal semantics of the guest OS. The tenant installs host agents in VMs that bridge the semantic gap and work in conjunction with the host. For example, security scanning and resource reclamation. However, CVMs block intrusive and direct host access to the guest, so the host-driven maintenance is failed. The CVM guest also denies the untrusted agent provided by the host, so the guest-driven maintenance is also failed. Current salvage introduces non-trivial modifications to the firmware or hardware by CVM hardware vendors. More functions are moved into the trusted firmware, and more interfaces are exposed to the host OS. Take the snapshot of AMD SEIEE as the example. These interfaces enable the host OS to extract CVM memory and states with encryption via the trusted firmware. Since the data is encrypted by the firmware, the host cannot compromise guest privacy. The host OS then uses the ciphertext to create an encrypted snapshot, or send the ciphertext to another host. The trusted firmware on that decrypts and inserts the plaintext into a new CVM instance so that CVMs can be migrated. However, this approach has 3 limitations. First, it lacks the flexibility to support the wide variety of customization services, primarily due to the slow updates for firmware and hardware. The lack of cross-platform compatibility also exacerbates this inflexibility, as these methods are confined to specific hardware platforms. Second, this approach enlarges the firmware's codebase and complicates its interactions with the host and the guest, making it more vulnerable to security breaches. Given that the firmware acts as the common TCP for the entire system, any reduction in its security poses risks to both the cloud providers and the tenants. Lastly, current methods cause performance issues in critical scenarios. According to our test, current AMD live migration solution based on firmware is nearly 2,000 times slower than normal VMs on the same machine, as shown in the picture. We found that the reason for this performance degradation is that AMD runs the trusted firmware on a special processor named AMD SP, which has very limited computing power. As shown in the right picture, the AMD SP only provides a throughput of 1.92 megabytes per second for CVM memory extraction and 1.86 megabytes per second for insertion. As the number of CVMs increases, this computing power is further shared out, resulting in the inverse trend as shown in the right picture. The low throughput also clarifies the migration results on the left, where the source and destination instances on the same machine would result in a throughput of only 0.93 to 0.96 megabytes per second on both sides. Consequently, the migration of the CVM with 2 gigabytes of memory takes over 2,000 seconds to complete. The limitations of current approach motivate us to question the validity of the current technique route and to explore a new design that meets 3 goals. First, our design should allow cloud vendors and tenants to flexibly customize and update maintenance models without having to suspend or migrate the VMs or even reboot the physical machine. Additionally, the design should ensure compatibility with all major CVM solutions without hardware modification. Second, the design should uphold the security of CVMs. The clear security boundary between the guest and the host must be maintained without new attack surfaces introduced for both sides. Third, the design should mitigate performance issues on maintenance modules caused by factors such as AMDSPs or guest workloads. The root cause of these limitations lies in the unsuitable choice of vantage point for maintenance modules. We argue that a more attractive option to explore is to put the guest-trusted maintenance modules into the CVM, especially since mechanisms like upcalls already exist for hosts to activate specific in-guest modules. But directly applying existing mechanisms to support in-CVM maintenance faces 2 challenges. First, these in-CVM maintenance activities can lead to performance degradation due to resource contention with the guest workload, potentially leaving the maintenance modules resource-starved when initiated by the host. According to our test, this can result in about a 3 times slowdown in resource reclamation scenarios. Second, certain maintenance tasks, such as disaster recovery, have strong fault tolerance requirements to work correctly even when the guest OS fails. But current methods fail to provide them with isolated execution environments. The key to addressing these issues lies in exploring a new mechanism capable of providing the host with the semantics of host invocation of targeted maintenance operations with separate and protected resources. We observe that while current CVMs limit the host's intrusive access to the guest's data plane, the hypervisor still exerts influence over the control plane. For example, host can still schedule vCPU threads. This observation inspired us a new idea that extends the semantics of vCPU scheduling into the semantics of host invocations of maintenance procedures. Based on this idea, this paper introduces confidential procedure calls, or CPC for short, a flexible, secure, and efficient mechanism for CVM maintenance. CPCs introduce extra vCPU threads for the host, which we called HVCPUs. HVCPUs do not participate in the standard host thread scheduling, and they are bound with maintenance modules. The host can invoke maintenance functions agreed and trusted by the guest by simply awakening and scheduling HVCPU threads. The core maintenance logic of a CPC is designed as a state machine driven by both the in-host control plane and the in-guest data plane. The host can activate this CPC state machine by simply wake up and schedule the corresponding HVCPU. The state machine is infinitely cyclic and supports being called multiple times under guest's permission. By splitting the control plane and the data plane, the CPC state machine maintains a clear security boundary between the host and the guest and reuses current mature mechanisms and interfaces, ensuring no security degradation on the CVM. Based on CPC, we first developed a snapshot model. and use it to compare the performance with current AMD solution. In the case of a single CVM, a software-only CPC implementation is 34% faster. But CPCs are scalable and do not slow down in 8VM scenarios. In the contrast, current solution is 8 times slower and 12 times slower than CPCs. We then further accelerate the encryption with AES-NI on x86, which results in a 340 times performance improvement in the single VM scenario, and still no degradation in 8 VMs, reaching a performance lead of more than 2,800 times. This improvement is significant. So, have we done? Does this design really work? No. The maintenance operations we need to support include critical operations like disaster recovery and error diagnosis. These operations are designed to help the tenant to rescue data or diagnose the problem when the guest OS errors. This motivates us not to just follow the CVM threat model, which completely trusts the guest OS. We must clearly recognize that the CVM threat model is inadequate. The guest OS is usually Linux, and its TCB is too large. There will be bugs or vulnerabilities. Therefore, the CPC solution must take into account that after the guest OS errors or even be compromised, how can CPCs not to be corrupted together? And instead, it will continue to run correctly and help users to diagnose errors and rescue data. So we must consider how to isolate critical CPCs from the guest OS. The AMD SEIEE has the VMPL feature, where we can run critical CPC logic on VMPL 0 and the guest OS on VMPL 1 or 2 or 3, so that it cannot attack the CPCs inside the highest privileged VMPL 0. Currently, HackT of Microsoft is using this hardware to protect some modules. But just like their CCS paper said, other new confidential VM techniques such as Intel TDX and ARM CCA lack a VMPL-like isolation inside their confidential VMs. So, will CPC design also be limited to AMD platforms, just like the previous work? No. Our goal is to enable CPC to be used on all CVMs. Let's go back to the beginning to review this summary picture for all CVM platforms. Is there a strange thing in this picture? Yes. The stage 2 page tables of CVMs use a red and black gradient color. This is because the S2PTs on AMD SEIEE are controlled by the red untrusted host, whereas the S2PTs for guest privacy memory on other CVM platforms are managed by black trusted firmware. Let's sort out the clues. The AMD SEIEE has a VMPL feature that allows for CVM internal isolation, but its S2PT is not trusted. Other CVM platforms do not have the VMPL feature, but the S2PTs for guest private memory are trusted. This difference gives CPC a chance to adapt to other CVM platforms. We seized this chance and proposed the confidential page table isolation technique, or CPTI for short. CPTI lets the trusted firmware configure separate S2PTs for HV CPUs of critical CPCs. These extra S2PTs have additional mappings for the CPC trusted memory, which are not accessible for the guest OS, so that the critical CPCs, or SECPC for short, can protect their code and the data in this memory. With SECPC's trusted stage 1 page tables and the interrupt vector tables built on the trusted memory, as well as the firmware's on-demand TLB flash and the CPC's innate HV CPU register isolation, SECPCs can achieve VMPL-like isolation on other CVM platforms to defend against errored guest OS. We have implemented CPC with CPTI and some simple maintenance operations on ARM-CCA. The analysis showed that CVM maintenance based on CPCs will result in compacting firmware, and it will not compromise the security of the guests. For the host, CPC also does not spike its TCP. But put these little points aside, I would like to separately emphasize that the root cause of CPCs being practical and secure is because this design maintains the clear security boundaries defined by the CVM and reuses existing mature mechanisms as much as possible. In our performance tests on the AMD platform, as just mentioned, there is a 340 times performance increase in snapshots, and it can be further increased as the number of VMs gets higher. In the memory reclamation scenario, if the guest is busy, then the existing solution will suffer from severe performance disruption, whereas CPC is able to maintain up to 3 times faster than current solutions. We further measured the overcommitting scenario, and the CPC gets more improvement. Finally, the line migration test. If CPC is implemented purely by software, it could reduce the migration time to 36 seconds, accelerating it by a factor of 56. With AES-NI encryption acceleration, this can be further reduced to 29 seconds, a speed up of 69 times. In order to explore the upper limit of performance that CVM can achieve, we assume that there could be a hardware to accelerate the encryption and the encoding process to the overhead of a simple memory copy. We tried this by simply removing the encryption and the encoding process and directly copy the guest memory, exposing the plaintext to the host. This achieves 16 seconds, giving a speed up of 123 times. When we migrate 2 CVMs at the same time, AMD's time consumption also doubles, while CPC remains unchanged. The more migrating CVMs there are, the more performance improvements in CPCs. We also compare CPC live migration with traditional VMs and found a few ways to further accelerate the migration. For example, CPC live migration can leverage multiple HV-CPU threads to extract and insert the guest data so that the performance can be improved exponentially. Also, in current implementation, CPC live migration just uses the pre-copy technique. It can also use post-copy migration for acceleration. To our surprise, current interfaces of AMD SP cannot support this because it forbids inserting memory into an already running instance. To summarize, we propose confidential procedure calls, which extend the semantics of vCPU scheduling into the semantics of host invocations of maintenance procedures. CPC's flexibility enables customized maintenance modules defined by the cloud tenants and the providers. The clear security boundary it maintains also upholds CVM's security. In several critical scenarios, CPCs can achieve significant performance improvements. So we can see that CPCs can support flexible, secure, and efficient CVM maintenance. In addition, our design is compatible with all current CVM solutions. This talk only shows the main idea of CPCs. More optimizations and details about CPC can be found in our paper and poster. Thank you for listening. Any questions?